Recording in progress.
Yeah, cams on everyone. Let's start off. The last thing we did a combination of we're doing non-idle batteries. Great. So before going ahead, let's do one problem. Then we'll go ahead with this. Let's say we have an RC charging circuit, capacitor, battery, and see this is empty. The switch is closed at T0. Plot power in the capacitor versus time graph. We have done this thing last time if you remember, power in a capacitor. Same thing, but an RC charging circuit. If I want you to plot a graph, approximately. Try. You got a minute or two. And people have not given the exam, please stay back after the class. Plot the power in a capacitor versus time graph. Remember last time we were talking about it. What is power in any element? It need not be a capacitor or a resistor. Don't use I square R. That's only for a resistor. So power in a capacitor is voltage across capacitor. Into current in the capacitor. Now this is an RC charging circuit where initially it is empty, so I can use my standard formulas. Q is equal to CV into 1 e power minus t by RC. I is dq by dt, that will be V by R into e power minus t by RC. Voltage across the capacitor is Q by C, and this is I. Multiply this, you will end up with V square by R e power minus t by RC e power minus 2t by RC. There, that's your power actually. Now, if you look at this function here, look at this. At t0, what is the charge? 0. Means initially power is 0. At t infinity, what is the current? Zero. Steady state में there is no current, so power is again zero. That means if you look at this capacitor at t0, there is no power. At t infinity, there is no power, so the power is increasing and decreasing. The value bumps up and then comes down. At infinity, again it becomes zero. Again, understand, power means how fast are you charging it. So we have to do maximum minima. So dp by dt is equal to zero. When you do this, you end up with minus 1 by rc e power minus t by rc plus 2 by rc e power minus t by rc is equal to 0. This comes out to be time is equal to rc ln 2. This is the time when the power is maximum. So if you actually try to plot this graph, the power would be zero at here, it increases and then decreases and becomes zero at infinity. And this peak value will occur at RC ln 2. So exam there'll be 4 options like same, but they'll change the time. They'll say RC ln 2, 2RC ln 2, RC and all that stuff. So if you don't know that maximum value, you can't draw the graph. So at this point, the capacitor is getting charged at the fastest rate. Is this clear, everyone? So it's a product of both the charge and the current. Clear? Last time we did something like this, but they initially had a charge. So you couldn't use these formulas directly. There you had to derive them that also. Any doubts on this? All got the graphs? Yeah, that's a bit about it. I thought let's do one more like that. Anyway, so last thing we did was non-ideal batteries. So non-ideal batteries also have an internal resistance. So they do mess up. The potential difference won't be equal to the EMF. Next thing, combination of cells. So today we'll be doing a lot of small topics. There are a lot of small concepts. Last class we did like one whole thing. First thing, series. So if we keep n cells in series, R1, E1, R2, E2, so on till Rn, En, you're keeping them in the same polarity. So negative, plus, negative, plus, negative, plus, and so on. The equivalent EMF, you can just add all the EMFs and you can just add all the resistances. So E equivalent will be sigma EI, R equivalent will be sigma Ri. Now, a kind of a theoretical question they can ask you. They did ask a question like this once. So we have n identical cells. Small r and d. A student accidentally connected m cells in reverse polarity. Find the equivalent EMF and the equivalent resistance. So we have n identical cells in series. So a student accidentally connected m cells in reverse. And this was a CT question. Meaning if I have to give you numbers, let's say you have 20 batteries and someone connected 3 batteries in reverse. Then what will be the new EMF and the new resistance? 30 seconds. Ne Devansh, ne Aditya, ne Vihan. Try it home. Okay, let's see. Got an answer? Type in the chat box to the co-host. So if you're connecting n cells in series, so this is n minus m cells. So you need to understand something. You lost m cells, but these m cells also went opposite to you. Let's say if you have 10 people in your team, 2 people left, and these 2 people became enemies, and they killed 2 more people in your team. You don't lose 2 batteries, right? You lose 4 batteries. 2 people went away, and those 2 cancelled another 2. In total, you use 4. So when you keep m cells in reverse polarity, you don't lose m batteries, you lose double the batteries, because every battery that got reversed will cancel 1 more battery. So this is in reverse polarity. So this can be replaced with n minus 2m into E. Resistance doesn't care how you connect it, it will be always same. Clear with that? So be careful, that double thing is important. That is in series, so not much in series as such. All clear? Next thing. Cells in parallel. So let's say you connect n cells like this in parallel to an external resistor. Let's say this is R1, E1, R2, E2, Rn, En, and this is R. So we want to find the maximum, what is the current in the external resistance. This is really not that a great formula, but yeah, let's see. Parallel to In, and let this current be capital I. So this capital I will be the summation of all these currents, I1 plus I2, so on till In. Now what you do, apply a Kirchhoff's law passing through one battery and through this capital R. So take a loop like this. So you get E1 minus I1 R1 minus capital IR is equal to 0. From here you get I1 is equal to E1 minus IR by small r1. Similarly, when I take the second loop, I'll get E2 minus I2 R2 minus IR. You get I2 is equal to E2 minus IR by R2. And so on, you do for all n loops. And now if you add all of them, on the LHS side, you can see it becomes I1 plus I2 plus IN. And this side, it becomes sigma EI by RI minus IR sigma 1 by RI. And I1 plus I2 plus IN is nothing but capitalized. If you bring all capitalized to one side and if you shift it, we get this is sigma EI by RI by 1 plus R into sigma 1 by RI. There, this is the current across the external resistor. By chance, if they ask you for the potential difference between the terminals A and B, VA minus VB will be simply IR. Not really a great formula. Like I never seen this thing being that useful. If you ever get this thing, you better do it again. But okay, parallel में that is there. But when you take only 2 batteries, you get a really decent formula. We will see that. But have a look at the derivation, how we did this. All clear with the steps? Great. Going ahead. Now, the next one, what you're doing, remember this formula. It will be quite useful. If you had only 2 cells, R1, E1, R2, E2 in same polarity, you can replace this with one battery, E equivalent and R equivalent, where E equivalent is E1 R2 plus E2 R1 by R1 plus R2. And R equivalent is simply R1 R2 by R1 plus R2. This is when you connect them in same polarity. You can just replace this whole setup with one single battery. Saves you a lot of time. Later on, we will see this thing in instruments also. So this whole combination behaves like that. If you reverse one of the battery, reverse polarity, R1, E1, E2, R2. This actually comes from the previous formula only, but only for two batteries, right? It resolves like this. If you put three batteries, the formula doesn't come like this. It becomes very messy. Reverse polarity plus minus, plus minus. You have just simply made E2 as minus E2. So we are assuming E1 is still dominating. If E1 is not dominating, the signs will take care of it. So E equivalent is E1. So the first one which you take, right, E1, that is you're assuming that battery is stronger. E1 R2 minus E2 R1. So if this value comes out to be as a negative, then E2 is actually dominating. R equivalent will be R1 R2 by R1 plus R2. Quite a useful one. Saves you time, at least at a mains level. Clear with this? Going ahead. So how will they frame a question on this? $10 battery, 2 ohms. So let's say we have a circuit like this. Let's say you have a capacitor here. Find the current in the resistor and find charge on the capacitor. And not a big thing. You could have done this. How will you do this thing? You can use junction law, or you'll say let the current be I. This is small I. This is I minus I. Then you write one loop here and one loop here and solve. That is how you do this question normally. But if you can use this equivalent battery, it saves your time. Get this? I'll give you 2 minutes. There's nothing there. Formula substitution. If you use the equivalent battery ka formula, which we have done just now. You can have a look at the formula in case you didn't write. If they're in the same polarity, it is E1 R2 plus E2 R1 by R1 plus R2. Try. Numbers are bad. Let's see. Yeah, so first thing when you do E equivalent here, I'm assuming the 10 volt battery is stronger. So 10 into 2 plus 5 into 5 by 5 plus 2. That's 45 by 7. R equivalent is simply 2 into 5 by 2 plus 5. 10 by 7. So you can replace this whole circuit with one battery and one resistor with the external R. This is 45 by 7 volts, this is 7 by 7 ohms, and this is 3 ohms. Therefore, current will be voltage 45 by 7 divided by 3 plus 10 by 7. You can leave it there. Same thing here when I do for this. Again, I'll assume 10 volt is stronger, so that is 10 into 2 minus 5 into 5. You'll realize you'll get a negative sign. This is minus 5 by 7 volts, meaning 10 is not stronger. It is actually the 5 volt battery, which is stronger. So the battery should be drawn like this. So that small q is not positive, small q is negative. So this was positive and negative, and this is 5 by 7 volts. So this charge which you got, so charge q is CV, which is 15 by 7 microcoulombs. So this charge is minus 15 by 7. This is 15 by 7. So in the question you said q, so q is minus 15 by 7 microcoulombs. So be careful which plate is positive. So that's what happens. I assumed the 10 volt is stronger, but the sign said no, it is the 5 volt which is actually stronger. So put the battery in the reverse. All clear with this? Then, so this thing kind of saves you time. Useful, that's it. So whenever you have two batteries, you can do this. All clear with this? If you have three batteries, you can actually do first two batteries, and then again you'll get two batteries. Again, you can keep doing that sequence. But that is as good as this only end of the day. Next one. Mixed grouping. This is important, right? Should definitely remember the result. I have seen this coming in different exams. Like if this thing keeps popping up somewhere or the other, even if you're doing HSC boards, I think this is also there as a derivation. So if you have n identical cells, are to be connected across capital R. So the question is the maximum current. How should they be connected for maximum current? So whenever they ask you a question, generally they'll assume it to be a symmetrical circuit, right? And they will give the numbers also that way. So the idea was this. Now see, if I keep all the batteries in series, I get very high voltage, but I also get very high resistance, isn't it? If I keep all the batteries in parallel, I will get less resistance, but I'll also get less voltage. So somehow, if I can balance both of them, so let's say you keep n cells in series, and like this, you create m branches in parallel. Again, we're assuming it will be symmetrical. And this total number of batteries will be n into m. So if you make a grid like this, so it is an n into m matrix kind of thing. This grid, you're connecting it to an external resistance R. And the question is this, I wanted to make this current maximum in this. Find small m and n. So that would be a question. That also can be a theory. Try, I'll give 3 minutes. Find m and n for maximum I. N is less than under root mn. I want the values when, right, Saish? Let's see. Nee, so that is not the answer. So remember what we did in parallel? We use that same logic here. Since here everything is in symmetry, let the upper branch give current I. Let this be I. Let this be I. Then this should be small m into I. Because if you add all of them, you'll get this. Now apply Kirchhoff's loop law through any one branch. You will get NE batteries minus I into NR minus I into capital R is equal to 0. So replace this. So this will be NE and this guy will be I NR by M minus IR is equal to 0. So we get I is equal to NE by NR by M plus R. This is E by R by small m plus R by N. And we also know capital N is equal to M into N. So let's replace small m. So small m, if you replace, you will end up with NR by capital N plus R by N. There I got the whole function in terms of small n. So to get maximum current, we need to minimize the denominator. Means we have to use maximum minima. So d by dn of NR by capital N plus R by N is 0. This would be R by N minus R by N square. You get N is equal to root over N capital R by small r. Check. And the small m becomes automatically root over N small r by capital R. Mathematically, this is a function. This need not be an integer. But yeah, Max is saying if you put this branches in series and parallel, you'll get an answer. Have a look at how we did this. This was the same technique we used in parallel, and once you got the current I in terms of small n, it's simply maximum minimum. Clear, everyone? So if I just put it down properly, right, in a more usable form, so you need to remember this result. So for maximum current, right, the small n must be, so n is m into n, small m is root over nr by small r. Small m is root over n small r by capital R. This is the number of batteries in series. This is the number of batteries in parallel branches, basically. Definitely remember the results. Save your time in the exam, or else you have to derive it again. Example, they'll ask you like this. Let's say we have n 100 identical cells. Small r is 2 ohms and capital R is 8 ohms. So if you substitute the value here, it will get 100, 8 by 2. That is 20 batteries in series. So you make a 20 into 5 grid and 5 branches. This will give you the maximum current. But let's say if you have something like this, n is 100, R is 3 ohms, and R is 27 ohm. Then what do you think will be the answer? Try, I'll give you a minute. If the number of batteries are 100, internal distance is 3 and external distance is 27, now what should be the grid for maximum current? Right, Vihan. Near, you have a better version. See, so when you do this, you will end up with n is equal to root over 100, 27 by 3. You end up with 30. This doesn't make sense. If you have 30, then the branches will be 3.33. You can't have a 3.33 branches. So then you need to see for this 100 batteries, if you see n into m, what are all the possible combinations you can have? You can have 100 batteries in series, one branch, 50 batteries in series, two branches. Then we have 25, 4, 25, 10, and 10. Among all this 30 is closest to 25 into 4, isn't it? That's your closest possibility. Because see, Max doesn't know about an integer. Max simply thinks it is a function, and it is simply saying the maximum value occurs here. But we know this function, we can take only the values which are integers like this. So the closest integer to the maxima will give you the maximum current. So practically that is the most efficient thing, but yeah, mathematically it says something else, but we can't use it. Is that clear, everyone? So the answer should be 25 into 4. So this is one important thing. So in this combination of batteries, right? This formulas, the two batteries ka combination and this mixed grouping, these are the two important ones. Especially for mains and bits, direct questions come. Now, if you know the result, it is like you will finish off in 20 seconds. People who don't know the result, they'll keep hitting their head like what happened, and it's a waste of time. Clear with this? Yeah, that's a little about combination of batteries. Then power produced in a resistor. So if you have a resistor R and if the current is I, power is simply voltage into current, which is can be written also as I square R, which can be also written as V square by R. Be careful, V is not the voltage of the battery, V is the voltage across the resistance. So heat per second is given by power into time. This is I square R dt. This can be also written as V square by R dt. You really don't have too many questions on this, but whatever questions you have will be all based on heat and thermodynamics again. We'll see a few of them. That's your straightforward formula. Clear? Let's say question. We have a resistor here, which is 10 ohms. This is a graph between current versus time. So current I is flowing through the resistor, and this current is actually a linear function. So current decreases linearly from 10 amperes to 0 amperes in 2 seconds. And if this current goes through a 10 ohm resistor, find the heat produced. So you have a variable current. Similarly, let's say we have R is equal to 10 ohms. Instead of current, someone gives you a charge. Charge is T square minus T. Find heat produced in 2 seconds. Right. It's just integration there. Brute force, there's nothing there. 500 by 3, 400 by 3. Let's see. First of all, the current is decreasing linearly. It's a linear function. You can write this thing as like I is equal to AT plus B. T is 0, current is 10 ampere, and when T is 2 seconds, it is 0. The slope is, A is the slope, which is minus 5. You can clearly see I is equal to minus 5t plus 10. That's your linear function. So heat produced will be integral I square R dt, 0 to 2 seconds. R is 10 and this is there, so 25, 250 will come out. And then you will have 2 minus t, that is 4 minus 4t plus t square dt ka integration from 0 to 2. That turns out to be 400 by 3 joules, I guess. Anyone got 400 by 3? Some Aditya got 400 by 3. So. Check it out, I don't know. 400 by 3 looks too small actually. That will be 4 into 2, 8 minus 4t square by 2. That is 8, so that cancels off. You'll have t cube by 3, 8 by 3, near 2000 by 3. Check your answer. Just an integration there, nothing. Same story here, I is dq by dt. 2t minus 1. So heat produced will be integral 2t minus 1 whole square into 10 into dt from 0 to 2. I will leave it to you. This much you can handle. Clear with the steps. 140 by 3, yeah? Okay, Anshu got 140 by 3. I don't know. You guys can check out the answer. And Anil's got 140 by 3. Yeah, Devansh also got it. Must be right. All clear with this? Yeah, 140 by 3. Easy. Next one. So there is just a function there. You put it there and integrate. There's nothing here to think. So we have an insulated container. We have an insulated piston. Mass is m. Area of cross section is a. The whole thing is an insulated container. Here you kept a resistor R and you're sending current I. This whole space inside is filled with helium gas of n moles. Outside we have atmosphere, P0 and temperature T0. Now what is observed when this current is passing through this? The gas gets heated. When the gas gets heated, the pressure increases. Pressure increases, it pushes the piston out. And it is observed the piston moves out with a constant speed. Find V. Like I said, it is more of a thermodynamics question. The only thing you did was I square R. Once you remove that, current is done. Try. You got 3-4 minutes. Hope the question was clear. It's an insulated piston, free to move. There is no friction. Insulated smooth piston. Mass is there, area is A. Container is also insulated, so all the heat is within that. It's going up with a constant speed V, find V. How do we start? Think. Take another minute or so, then I'll explain you what is happening, and then I'll get another 2 minutes. You got velocity in terms of velocity, mg plus p naught a into v is velocity. Let me help you with one thing. Say, ask yourself this question: whatever heat that I'm supplying, where is this energy going? Should always start from there. Like, I'm giving you energy, great, but what are you doing with this? So whatever heat that I'm supplying, now see, when this piston goes up, you're increasing the height, so there is a change in gravitational potential energy. Agreed? Plus the temperature of the gas is increasing, so there's a change in internal energy. Plus you're compressing the atmosphere, so there's a work done on atmosphere. Plus change in kinetic energy of the piston. Luckily, piston is going with constant speed, so change in kinetic energy will be 0. Does the energy go anywhere else? Since the whole container is insulated, nothing can escape, so that is gone. Think about it. Can you use this energy anywhere else? Use it to increase the height, use it to increase the speed, use it to increase the temperature inside, and use it to push the atmosphere outside. That's it. And delta K is 0. So these are the 3 terms. And heat produced is nothing but I square R dt. So if you take small time dt, whatever heat that you're supplying will be used for changing potential energy, gravitation, change in internal energy, and work done on atmosphere. Now what? Think. You get a big answer, right? You guys didn't get anything. You guys didn't even use helium ka value on this. How did you even get your answers? Helium also absorbs some of the heat. All the energy is not just used to push the piston. That is the main catch actually. Whatever heat I'm supplying, where is it going? If you ask yourself that question, then you will see where is this energy going. Start from there. What is T record? Okay. So do you even read the question? Did you understand what you read? So if something is changing with time, can you say it is constant? Think na, it's okay if you don't get an answer, but when you're giving a blunder, at least know you're doing a blunder. Again, Puroja, same thing. Did you even use CV? Helium ka molar heat capacity, you used it. Okay. Let's see. And maybe you're right. We need to check. Maybe 3R by 2. I think you're right. Puroja got it. This would be a pretty good, more than one choice question. Do you know what kind of process the gas is undergoing? That itself is a question. I'll ask you, find the speed, what is the process the gas is undergoing, find the temperature inside the gas, find the change in temperature as function of time. I can ask you a lot of stuff. Yeah, right, Purada. Let's see. So let's say this piston, right? Let this distance be x, and in time dt, let it go dx distance. So take a very small time dt. Let piston move by dx. So during the small time dt, whatever heat that you supplied must be used for changing gravitational potential energy plus change in internal energy plus change in work done on atmosphere plus change in kinetic energy. Luckily, this guy is gone since the speed is constant. So in time dt, the heat supplied will be I square R dt. So at this point, current electricity got over. What is change in potential energy? mg dx, because it went up by a height x. What is change in internal energy? ncv dt. dt is the change in temperature of the gas. What is work done in atmosphere? P naught into area into dx, pressure into change in volume. Clear with that? If you see dx by dt is the speed, isn't it? So if you send dt that side, I will get I square R. This will become mg dx by dt, which is the speed which I want. ncv dt by dt, this is where I'm got stuck actually, dt by dt. This is p naught a dx by dt. So I need to find dt by dt in terms of velocity. So how do we do that? So for that, let's see the next page. If you draw the FBD of the piston, if you look at the forces, we have P gas into area, we have the atmosphere pushing you down P naught into area, and you also have mg. So if you actually see the pressure of the gas, technically speaking, this, if it has an acceleration a, this is 0 because v is constant. If v is not constant, this problem would have been very messy. You will get differential equations. So we'll get P gas is equal to P naught plus mg by A. And if you observe, this is constant. This is an isobaric process. The pressure never changes. Okay. Then we can use an ideal gas equation. P gas V is equal to nRT. So pressure of the gas is P naught plus mg by A. Volume is nothing but A into dx. I can differentiate this, and this will be nR into dt. There, from here, if I put dt on both the sides, I'll get P naught mg by A. Just multiply that A inside. P naught A plus mg dx by dt is equal to nR dt by dt. So basically, I differentiated here. There, I found the rate of change of temperature also. So I can find the temperature as function of x, where x is the distance traveled, which is nothing but Vt. So I can play like that also. This guy would be P naught A plus mg by nr, and this becomes velocity, dx by dt. Clear with that? Your ideal gas equation. Check your steps. So once we got this, let's take it and dump it here. So this guy will be I square R. This will be mg plus ncv. Cv is 3R by 2 for helium, and this will be P naught A by plus mg by nr. This also becomes velocity plus P naught A into velocity. There, you got everything. Just shift it there. You'll get an answer I square R by mg. What is Cv? Nn will cancel. CV is 3R by 2. So that will be 3 by 2. So we get 5 by 2 mg plus P naught A. Yeah, perfect. So 2 by 5 I square R by P naught A plus mg. Did someone get this? It looks like someone got something like this. Nah, I guess forgot mg, I guess. Yeah, something I guess forgot. Other steps clear, everyone. Any doubts on this? So the main thing is asking where is all this energy going, I think. From there, you start asking and you get it. Any doubts on this? All clear? Take a small break, come back in 5 minutes. Any doubts so far? Chalo, come back in 5 minutes. Next thing. So we got a cylindrical resistor here. Connected to a battery. The radius is A, length is L, rho is the resistivity. E is the coefficient of emissivity. Radiation, everyone. E is equal to 1 for black bodies. Outside is vacuum, so you can take outside as 0 Kelvin. So if you switch on the resistor, what will happen? It will produce heat. If it produces heat, it will start radiating heat. So temperature will keep rising. At some point, it will reach a steady state. Find temperature of the resistor in steady state. Neglect any conduction. It's a big one. Matlab, it's easy to solve. The answer might be bad. Think. I'll give you another minute. You get something big. Let's see. See. The idea is pretty simple here. So whatever heat you're producing must be going out in the form of radiation. Heat produced by resistor must be equal to the heat radiated by the resistor since you're in steady state. No, it's not a big thing, but there's one small mistake people do here. What is the power produced in a resistor? V square by resistance, which is rho, length, area. Now be careful. In the formula rho L by area, what is this area? This is cross-sectional area. V square by R ka formula. And here, when you use Stephen's law, sigma A E TB power 4 minus T surrounding power 4. Remember this formula? This T surrounding will be 0 because it is 0 Kelvin. What is this area here? This is the surface area. Be careful, don't cancel both the areas. So this area goes up to most people cancel this area and this area. So this A is the surface area. In the resistor, that is the cross-sectional area. And what is the surface area? So this surface area is 2 pi R 2 pi A into L. That is your curved surface area plus 2 pi A square. There are two disks also, no? You have to include this disk area also. So this will be the curved surface area. This will be the disks. Yeah, solve this, you'll get the temperature of the resistor. Clear with this? It's one equation, but you should know that you're relating it to the heat transfer, radiation and current electricity. Clear with this? Let's see one more. Sigma is what? You forgot sigma? And sigma is not charge density record. Value yaad hai? It's one of the easiest one to remember. 5, 6, 7, 8. Let's see one more easy one. Let's say you have a container filled with liquid. Identical containers, they have same amount of water. Case 1, you took two resistors. You kept them in parallel and connected to a battery. R1, R2, V. In case 2, you kept them both of them in series, R1, R2, and you connected them to a battery. In the first case, it took 40 minutes. It took 10 minutes to boil the water. Here it took 40 minutes to boil the water. Find R1 by R2. So two resistors are placed in parallel and then connected to a thing. So using as a heater. Did you ever use an immersion rod? Immersion rod is simply a heater. Let's get this. This is an easy one. Right, Vihan. Yeah, right, Puruja. Right, Kush. There are three answers. Straightforward. See, what is there? Since you're boiling them, the amount of heat must be same. They should have same heat to boil the same amount of water. Heat is nothing but power by time. So this is V square by R equivalent is R1, R2 by R1 plus R2. That's your power in the first one into time is 10 minutes. This should be equal to second thing, V square by R equivalent is R1 plus R2. Time is 40 minutes. If you solve this, you will end up with R1 plus R2 whole square is equal to 4R1 R2. This is R1 minus R2 whole square is 0. R1 is equal to R2. 1:1 ratio. Easy. Since the containers are identical, they have same amount of water, they require the same amount of heat to boil. But both of them are producing different amount of power, so power into time is constant. Any doubts on this? Next one. Next one. Let's see one small theoretical thing. Now, if you have a bulb, and let's say you have a bulb whose filament is non-uniform. The area is something like this. So you made a filament like this. This is connected to a battery. So this cross section is A and this cross section is B. So filament of a bulb is made of a wire of non-uniform cross section. And now what happens? Normally, this is what actually happens with the bulbs. These bulbs really produce really, very high temperatures. Almost they reach around 4,000 degrees. So because of that high temperatures, right, the filament starts vaporizing. Due to the heat, the filament vaporizes. And eventually it will break at some point and the whole thing gets disconnected. And finally the filament breaks. At that point, bulb will stop working. So first question. So during this process, how does the brightness vary? Options will be like this. The brightness will increase, 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 and then suddenly stop. The brightness will decrease. The brightness will increase and decrease. Will brightness will decrease and increase, something of that sort. How does the brightness vary? Compare the temperature at A and B. So on this filament, if you take the 2 points A and B, who do you think will have more temperature? Or do they have same temperature? I can ask you a lot of things. Which point is more susceptible to break? What happens there? What happens here? How happens to the brightness of point A? So you can keep asking questions. Think, think, think. Take a minute and so I'll show you that. A completely theoretical question. PA is greater than TB. What about the brightness? Let's see. So what actually happens here? And this is not the first time you're doing this. You have already done this. You guys don't realize it. Yeah, the question. This was the same question. So what's happening here? So when you take this filament here, the current I will be same. And do remember the current I also depends on the resistance. Now, if you look at the resistance here, R will be rho L by area. So resistance is proportional to the area of cross section. So resistance at point A is greater than resistance at point B. Now, because the resistance is more, the heat produced, current is same, I square RA is greater than I square RB. Since the heat per second is more, temperature will increase more. So point A, if you see the temperature is more than B, heat per second at A is greater than heat per second at B for a given thickness, for a given length. That means you have to emit more energy out, so you need more temperature, isn't it? Radiation, just now we saw. If you're producing more heat, you need more temperature to emit. Therefore, temperature at A increases. But the moment temperature at A increases, it starts melting faster. If it melts faster, it becomes thinner. If it becomes thinner, the area will decrease. So you'll get more resistance. If you get more resistance, you will produce more heat. If you get more heat, your temperature will increase more. You got how it became a cycle? So eventually, point A breaks. So in a non-uniform wire, the thinnest spot is the weak spot. And that point will be like pretty bright. Matlab, that point ka brightness will just keep on increasing. But there's a small catch. Brightness of A increases. Matlab, if you just look at the whole wire ka comparison, the point A keeps becoming brighter and brighter. But the overall bulb, if you see, this is RB and this is RA, whatever, the overall resistance increases. Since filament becomes thinner, resistance increases. Now be careful, don't use I square R because I is also changing. We use V square by R because voltage is constant. V square by R proportional to 1 by R. So bulb actually, power decreases, bulb actually becomes dull. So the overall brightness is decreasing, but A will actually keep glowing brighter. Therefore, bulb becomes dim. And then it just shuts down suddenly. Clear with this? What you must have thought is resistance is increasing, so I square R is increasing, isn't it? But you're forgetting even I itself will change, isn't it? What remains constant is voltage. Is that clear, everyone? Yeah, generally, this is what happens with the bulb. We don't face this kind of problem. We use LEDs now, so you're kind of safe. All clear with this? It's a good one theoretically. If you ever seen these old bulbs, you will notice inside the bulb there is a kind of a silver coating here. The bulbs sometimes have that, shaded thing. So that is actually the filament which got vaporized and got stuck to the glass. If the bulbs are really old bulb, if you see, you'll see. But I don't think you guys must have seen bulbs also anytime recently. Right? So it is like an antique thing. Nowadays, IKEA, they sell bulbs as if like it's a decorative item. So that way. So that is a little about the bulb. Now, since we talked about the bulb, let's talk about that. There's the next part. Bulbs. Ever been to a shop and you ask him, give me a bulb, or went to a mall and try to get a bulb? What is the first thing the shopkeeper will ask? What power you want? 10 watt, 15 watt, 4 watt, 20 watt, something of that sort. So every bulb that you see, right? Forget about the bulb. Even the adapter that you're using for your mobile or anything, you can see that there is something called rated voltage. So it will be like this: rated 220 volt, 4 watt. It will be written like this. So what is the meaning of the symbol? The meaning of the symbol is, if we give 220 volt, then we get 4 watts of power. That's what it is saying. It is not saying you should keep it only across 220, right? Or you'll always get 4 watt power. If you keep this bulb across 220, we get 4 watt ka power. Now in India, we use 220 volt supply. So when you go to the shopkeeper and ask him, give me a bulb, he won't ask you what is the voltage. It is understood you are going to use 220. So we just talk about power. So power is equal to V square by R. So indirectly, you can find the resistance of the bulb. So R is V square by P. And V is your rated voltage. That means if you buy a bulb in India and take it to US, now in US, the power supply is 110 volts. They don't use 220. Sit straight, everyone. Sit straight. This is not a movie or theater, right? So focus. Small things. When you don't respect the subject, when you don't respect the thing, then the subject also will make sure to mess up you big time. It starts like that only. So if you have a bulb, let's say you connect a 110 volt supply, but you brought a 220 volt bulb, 4 watt. So if you take a bulb in India and you connect it in the US ka power socket, now remember the formula for power is V square by R. So this V is 110 square, and this is 220 square by 4. Remember, the meaning of this thing is if you put 220, you get 4. It doesn't mean you can't put anything other than 220. This is going to give you 1 watt. So an Indian bulb in US will glow at 1/4 of the brightness. Okay? It doesn't mean it will not work at 1. It will work at 1 and give less brightness. I can even put 440 volts. It will give you 4 times the brightness. So the bulb has no issue as such. It will give any voltage, it works. But it won't give you 4 watts anymore. Clear with the concept, the meaning of rated voltage. Long back, when I used to stay with my friends, the bulb in the hall went off. I went to the shop and I thought, yeah, I will. And the room used to be pretty gloomy and dark. I said, I'll get a good bulb. I'll get a very high powered bulb. I went and said, I really didn't know how bright it was. I said, give me a 100-watt bulb. You know how bright is 100-watt bulb? You literally become blind. That guy was looking at me weirdly, but he said, okay, you want 100 watt, I'll give it. I took a 100-watt bulb. I installed it. I switched on the light and shit, I couldn't see anything for 5 minutes. I had to switch off the bulb. I had to literally got blinded. Stun gun bolte na, something of that sort. And then I said, this is fun. So I just kept the lights off. I went and hid in my room. I was waiting for my friends to come. So we are playing that full game that if people are coming, switching on the light, they get flooded. They become blind for 2-3 minutes, shouting, jumping, anything. So yeah, and that will we saved it, to torture people during the night sometimes. So let's see a question. It was bad. If someone had any problem with that lighting thing, they'll get fits and all. But the best thing, when it hits so hard, right, you become temporarily blind for 1 or 2 minutes. You'll panic a lot. You think like, what the hell happened? So let's say a question. So you have taken two bulbs. Normally in the house you use like what? I think these are like 15, 20 maximum, 24 maybe. So we got two bulbs here, bulb A and bulb B. So this bulb is 220 volt, 4 watts. This bulb is 220 volt, 2 watts. Which bulb glows brighter? Again, don't see that 4 and 2 and get misled. If you apply 220, it will be 4. But when you keep two bulbs in series, the voltage will not be divided equally. So find the ratio of power of A and B. Get this is an easy one. So using those numbers, you can always find the resistance. That is the main catch. Resistance of a bulb is rated voltage square by power of the bulb. Let's get this. One is to two. 1:2. Yeah. So when you get these kind of questions, right? See, I'm asking for ratio of power. So we are not actually interested in the amount of power. So let's find resistance of A, which is 220 square by 4. Let's call this thing R. Resistance of B is 220 square by 2. Let's call this thing 2R. So just let's redraw the circuit. So this guy will be R and this guy will be 2R, A and B. Since both are in series, same current will flow. So power at A is to power at B will be I square R is to I square 2R. 1:2. So the bulb B actually glows 2 times brighter. The problem here is the voltage will divide based on the resistances, isn't it? So the voltage will not get equally divided between the bulbs. So bulb B actually gets lesser voltage, more voltage than bulb A. No, other way around. It gets I square R. Clear with this? Let's see a better one than this. A, B, C, and D. Let's say this is 220 volt, 4 watts. 220 volt, 2 watts. 220 volt, 4 watts. 220 volt, 2 watts. 4 bulbs. Find PA, PB, PCD. Find the ratio of power of bulb A, B, C, and D. Get them. And if bulb C gets shorted, what happens to brightness of A and B? Or gets burned, or whatever you want to call it. So bulb C was lost, meaning it became an open circuit there. Then what happens to the brightness of the bulbs individually? What happens to brightness of A? Increase, decrease. Brightness of B, increase, decrease. Brightness of D, increase, decrease. ऐसा. First get the first part. Then let's see the second part. Right. Give it a try. I'll just get some water and come. Let's see. What did you guys get? 25, 18, 4, 8, 25, 8, 19, 19. Yeah, something like that. So let's see. So let's just redraw the circuit. First, find the resistance of the bulbs. Distance of A and resistance of C will be 220 square by 4. Let's call it R. Resistance of B and resistance of D is 220 square by 2. Let's call it 2R. This is R. Two R. R and 2R. Now, like I said, we are not actually interested in the value. So let this be I. Here the current will split. This is 2R and that is 3R. It will split in the I1 R1 is equal to I2 R2, same voltage. So 3:2 ratio. So this will be 3I by R 5 and this will be 2I by 5. Got this? That's how the current splits. So then you're done. So power at A is 2, power at B is 2, power at C is 2, power at D. This is I square R. This is 9I square by 25 2R. 4I square by 25R. 4I square by 25 into 2. So this will be 25 is to 18 is to 4 is to 8. So bulb A is the brightest and C is the least. Clear with this? Question is not over. Now, if the bulb C gets disconnected, what happens to the brightness of the bulbs? Let's get that. I'll give you a minute for that. Try everyone. Not straightforward. No, I didn't ask you the ratio. I'm asking you what will happen to the brightness of bulbs. That means you're comparing the brightness before and after bulbs he got shorted. So the problem with that is the current in the circuit itself will change, isn't it? You don't get the same current in both the circuits anymore. So you actually have to find the current now. So this is R, this is 2R, this is R, and this is 2R. This was the initial situation. R equivalent was how much? 3R 2R, 3 to 6, 6R by 5 plus R, 11R by 5. So this current that went here, I1, was 5V by 11R. This is I1, and this thing was 3I1 by 5. Now, after the bulb C got shorted, the circuit became like this. So D will completely shut off. So D is gone. Now the current becomes I2. The same current I2 also flows here. So now the current I2 will be V by 3R. So now we are comparing A ka brightness before and after. Before and after. So before it was power what? I1 square R. Now it was I2 square R. R goes off anyway. So this thing will be 25 by 121 and this thing is 1 by 9. Which is bigger? That is 9 into 25. 175 is to 121. So A became dim, right? So you have to compare before and after shorting. You're not comparing A and B. So if you look at B, same thing. This would be initially 3I1 by 5 whole square by 2R is to I2 square by 2R. Resistance cancels off anyway. So this will be 9 by 25 into I1 square is 25 by 121. Is to I2 square is 1 by 9. 81 is to 121. B actually becomes brighter. So compared to the before shorting, B becomes brighter. D will shut off, A becomes dull. Is that clear, everyone? You need to find the currents now. If it is only comparison between the bulbs, it is easy. But if you ask before and after, then a little more work is involved. All got this? It's a good one. Next one. Any doubts on this? Arnav, Kush, Pushkal, clear with this? Suhan, clear? Adi? Next thing, bulbs in series. Let's say if you bring two bulbs, 2 watt and 4 watt, and if you keep them in series to a 220 volt supply, then the question would be like this: what is the total power produced by the bulbs? Now be careful, I told you those 2 and 4 watts are misleading. If you don't give 220, you won't produce that power. And when you keep in series, they won't get the same voltage. So if you keep the bulbs in series, P1, P2, and Pn, we know the resistance are equivalent. Resistance adds up R1 plus R2 plus so on till Rn. And we know resistance is equal to V square by P. So resistance is proportional to 1 by power. So if we keep bulbs in series, the total power will be 1 by P1 plus 1 by P2. They will act like capacitors reverse. So if you put a 2 watt bulb and a 4 watt bulb in series, the power you will get is 4 into 2 by 4 plus 2. You won't get 2 plus 4. If you keep bulbs in parallel, then the total power will be P1 plus P2 plus so on. Clear with this? Till now, how many times the series parallel thing came? Do you guys remember? When was the first time you saw something like the series parallel thing? First time you saw this was in springs. Springs in series, springs in parallel. Then you saw in heat transfer, conduction, thermal resistance. Then you saw it in viscosity, Poiseuille's equation. Then capacitors, then resistors. Now bulbs. 6 times you have seen this. This kind of combination circuits and all that stuff. Clear with this, everyone? The next thing, maximum power transfer theorem. Like I said, we had a lot of small things today. So the question comes like this. So if I have a battery with an internal resistance, and how much resistance should I keep in series, or what should be the resistance of my device so that I can get maximum power from the device? The problem is whenever you're extracting power from a battery, this internal resistance is good for nothing. It actually dissipates energy, which you don't want, isn't it? That is a wasted energy. So the question comes like this. What is the maximum energy, maximum power that you can get from a system? So here R is your internal resistance. Capital R is your external resistor. So all the heat that you produce in small r is all energy in the internal resistance is wasted. You cannot recover that, and that actually heats up your battery. Kind of what happens when you're charging your mobile phone. It gets heated up because all that internal resistance produces heat. You can't do anything about it. That heat is always there. So the question comes this way, then what is the maximum power I can generate in this external resistor? So we know current is E by R plus small r. So power in resistance R will be I square R, which is E square capital R by R plus R square. So we do maximum minima, dP by dr is equal to 0. You end up with the result R is equal to R. Standard result, remember? So, but be careful. I'll show you how people goof up this thing. So when your external resistance, again, listen to when external resistance is equal to the internal resistance, we get maximum power in the external resistance. Now see, if R is equal to R means what? The internal resistance and the external resistance are producing same amount of power, isn't it? That is actually pretty sad, actually. That means even if you take the most efficient battery, you can't get more than 50% power, isn't it? 50% is always wasted. This is the reason why we don't use generally batteries, for long-term storage purposes. One of the biggest problem that we have in power supply and power distribution thing, we cannot store electricity. Currently, the power that you're using to watch this, lecture is being generated somewhere in some power plant at this instant. That this actually leads to a lot of problems. Think about it. If you take a city like Mumbai, right, and now see every city, right, the amount of power you can generate is fixed. For example, let's say Mumbai has a capacity of 5,000 megawatts. Now the problem is what? If you roughly try to draw this, let's say early morning, 4 o'clock, 5 o'clock, people are sleeping. Maybe the power consumption is only 1,500 megawatts. But as becomes, morning 7 o'clock, 8 o'clock, people are getting ready to offices, trains are going, offices are starting, the power consumption goes to around maybe 3,000 megawatts. By 11 o'clock, 12 o'clock, it starts getting heated up. People are switching on ACs, industries are working at full force. Around by 3 o'clock, right? Generally, 3 o'clock is the hottest part of the day. The value is peak. Maybe we are using around 7,000 megawatts. Now we have a problem. You need 7,000 to run the whole area, but I only have 5,000. So what do you do? Ever heard the word load shedding? If you ever been to your village or something, you will see in summer, they cut off the power supply in the daytime. So they cut off the power supply in the rural areas. Let's say Palghar or Kopoli or Panvel. They call it load shedding. They cut off the power supply there so that you can get the 2,000 ka deficit. So they cut off for 2 to 3 hours in Panvel, then they cut off in Palghar, then they cut off somewhere, and so on. So if you have been to a village, right, during summer, you will see this thing. You're like these idiots cut off the power supply exactly in the afternoon when it is very hot. And the power supply comes back again by evening 4 o'clock or 5 o'clock, if you have ever noticed it. By evening, again, the power supply goes down, and by evening 7 o'clock, people start watching serials and all, it might go up a bit and then starts dropping. So this is the problem. Now, the problem that I'm facing here is during night time, our generators are just sitting idly without doing anything. So during night time, somehow I can generate electricity, store it, and use it in the daytime. That would have solved our problems. Now, storage is a problem. So the problem with the battery is every time I try to store 100 watts, I can only store 50 watts. And when I try to recover, I lose again 100, again 50%, I get 25 watts. You're getting the problem? Storing, I lose half. Recovering, I lose half in the most efficient batteries. In real life, you won't even get 10% out. Too much wastage, not efficient. So we don't actually have a proper energy storage solutions. So people are trying to come up with different ways. One of the idea was this: use this all excess electricity to do electrolysis of water and create hydrogen and oxygen. And you can use hydrogen fuel cells and combine hydrogen and oxygen, and you can get electricity and water back. This thing gives you around 70% efficiency. But the problem, hydrogen is flammable. The circuits get burned sometimes, you can get an explosion, storage is a problem. Technology is still in the nascent phase, you can't really store so much. So yeah, a lot of problems. So that is one of a kind of a problem. So we produce a lot of electricity, but we don't know how to store it. So cost is always the main issue there. So let me show you a question how they'll frame on this. Let's see, fall into the trap. Let's say we got a battery with a 5 volt, 2 ohm resistor. We connect a 3 ohm resistor and we connect an R. So this 2 volt and this 5 volt are a part of a battery. First, let me ask you one question, then I'll ask you the second one later. Find R for maximum power in 3 ohms. Let's try this. What is the answer? I'll tell you what people do. Huh? This is the argument. Okay, now see, this 3 ohms doesn't know who is internal and who is external, isn't it? So the 3 ohms will think 2 and R is internal resistance. And from the maximum power transfer theorem, so 3 should be equal to 2 plus R, therefore R is equal to 1. This is a blunder. Because, go back to the question again. See, look at the statement. When R is equal to R, that means when external resistance is equal to internal resistance, you get maximum power in external resistance. The question is this, what should be my value be to get maximum power in my resistance? But what am I asking here? Find the value of R to get power in some other resistance. Are you getting this? That formula is not valid for this. The question should have been this. Find R for max power in R. Then you can use maximum power transfer theorem. Are you getting the difference between both the questions? I'll give you the first one, but you'll do the answer for the second one, and that option will be there. So how do we do this? So best thing, in case you get confused, just go back to the derivation. So what is the current here? I will be 5 by 5 plus R. So power in 3 ohm resistor will be I square R, which is 5 by 5 plus R whole square into 3. You can clearly see here, there is only one denominator, so R is 0 for maximum power. So if you want maximum power in 3 ohms, just make R 0. But in case of R, this will be 5 square by 5 plus R whole square into R. Here, it's a maximum again, maximum power transfer theorem. dP by d is 0, we'll get R is equal to 5. Hope you're getting the difference between both the equations. R is equal to R will give you maximum power in capital R. But the first question is find R for maximum power in 3 ohms. That has nothing to do with maximum power transfer theorem. Is this clear, everyone? So 0 is the answer for the first one. So be careful. Got this? Next one. The last small concept, fuse. Ever heard about this thing, a fuse wire? A fuse actually is a safety device. I don't think you must not have seen anything like this nowadays. We use all this, PCBs and this semiconductor things. So anytime in a house, there's a short circuit, the PCB switch just simply comes up. You must have done that. You go and put it back and everything is fine. But long back, 10, 15 years back, people actually used to use this, physical hardware. It's a safety device which disconnects when large current flows through it. So if there's a short circuit in the house, a large current is flowing through the devices. In order to protect them, you want to disconnect the whole power supply to the house. So this is one of a fuse that you use for smaller devices. It would look like this. This is how it kind of looks like. You can see the wire here. This is called a fuse wire. So the idea is this: when a large current flows through this wire will melt. If the wire melts, the circuit gets disconnected. So the whole power supply to the house goes off. Perimeter one, but people we used to use this. Even I still remember when I was in school also. Ever seen this thing? You have plugs like this. I don't know whether you have seen this thing. They still use this for big transformers. You have a big, ceramic plug. You put that plug and everything. So this plugs, actually have a wire passing like this. So this is your fuse wire. Anything happens, this gets disconnected. So what you have to do, once the wire burns down, you have to get a new fuse wire and you have to connect it and then put the plug back again. Then it starts working. So basically, this is like a one-time use. Every time fuse wire goes off, you have to buy a fuse wire and reconnect it again. So it was a headache. Getting it? So when I was in school, one day what I did, as usual, I used to be very curious. You know the power supply ka plug? I took a tongue cleaner, metal wala. I kept it inside these two, and I switched it on. Getting it? What I did? Yeah, I short circuit, isn't it? I kept a power supply with a zero resistance. You got a huge current flowing through this. The fuse wire gone. The circuit board got burned also. The switchboard and all. I though was scared. I just took out the tongue cleaner, threw it in the dustbin. I went outside and like, oh, something happened. You know how we act. Oh, something happened here. Oh, what is this? Oh, something bad. Karke. And my mom was wondering like, अरे क्या हो गया and all. So someone was saying fuse ఎగిరిపోయింది, fuse ఎగిరిపోయింది. So in Telugu, right, ఎగిరిపోయింది means fly. It flew away. It comes like that also. In a slang meaning, it's a way of saying fuse ఎగిరిపోయింది means fuse got disconnected. And I was there wondering like, yeah, fuse ఎగిరిపోయింది matlab this thing flew away. And I was a kid, what I was thinking? That means I thought there's a small bird inside that meter which is producing power. That bird got angry and flew away. Now I was thinking, how will my mom go and catch the bird? Later on, I came to know bloody fuse is actually a small wire, not a bird. You can be really dumb when you're a kid. The, so normally this is a symbol for a fuse, 10 amperes. So if you see a number like this, the meaning of this is if the current exceeds 10 amperes, circuit gets disconnected. Now we don't use these things anymore because these are one-time uses. So, but let's say if you are using a wire, tell me one thing. What kind of material should I use to make this wire? So the question will be like this. Fuse is made of a wire. Should it have a low melting point or high melting point? Ask yourself. When there is a short circuit in the house and the current is flowing in this thing, do you want it to melt fast or melt slow? Melt fast. So you need low melting point. You want it to melt at as low temperature as possible. Low specific heat capacity or high specific heat capacity? Should have a low specific heat capacity or high specific heat capacity? Ask yourself, what is specific heat capacity? Remember the formula? Q is equal to ms delta T. So delta T is proportional to 1 by S. Remember that graph which we drew? That means higher the specific heat capacity, more difficult to change the temperature. So ask yourself, you want the fuse wire temperature to rise fast or rise slowly? You want it to rise fast so that it can reach the melting point fast and melt. So you need low specific heat capacity. The low specific heat capacity will, the temperature will rise even for small heat. Clear with this? So you can frame theoretical equations of that sort. Got this? Let's just do one question. Let's say you made a weird combination with the fuse wires. 10 ohms ka fuse wire and you kept it in parallel to another 5 amp ka fuse wire, which is 5 ohm like this. So the question is find the maximum I so that both the fuses work. I don't want any one of the fuse to burn. So what is the maximum current that I can send so that both the fuses work? Let's get this. Finish off. Last one for the day. Right, Vihan. Right, Om. Right, Puraj. So the main idea, see, the current will always split in the ratio of resistances. It doesn't care about the fuse ka value. Opposite resistances. So this is I1 into 10 is equal to I2 into 5. So I1 by I2 will always maintain a ratio of 1:2. And now we have two possibilities. Since you're asking maximum current, meaning one of the fuse is having maximum current. If I assume the 10 ampere is having maximum, then I2 should be 20 ampere. This is not possible. I2 will blow off. That means the only possibility is I2 must have been maximum 5 ampere. Then I1 ka value is 2.5 ampere. Yeah, you're still safe. The maximum current you can have is 7.5, so that both are safe. Making sense? When you ask maximum current, one of them is maximum. We don't know whom, so guess both. Is this clear, everyone? Yeah, like I said, we did a lot of small things today. We saw the combination of batteries, series, parallel, especially this was important, the polarity, two batteries ka thing, and then mixed grouping, then power in a resistor. These are good questions based on, heat transfer and thermodynamics. Filament ka theory, bulbs, then we saw series, parallel, power transfer theorem, fuse, like a lot of small concepts. That is all one. So next thing that is left is, instruments. Quite an important thing, has a pretty good weightage because it comes in two parts. You can call it as current electricity, or you can also call it as electrical, instruments and, the instruments in the portion. So advanced portion, they gave it as two parts. Instruments is separate and the current electricity is separate. So we will be doing that. So quite an important thing. We'll be doing what is a galvanometer, ammeter, voltmeter, meter bridge, all that stuff. Quite important stuff. Mostly we should be able to wrap up next class, or it might spill over a bit. But next week we'll be starting off with a new chapter. After this, we will go with ray optics. Is ray optics done for most of you? It's an easy chapter, so we will go with that because magnetism and all. Let's take a small break from current. We'll go to ray optics, finish off, and then come back to magnetism. So it's a good chapter. It is not tough. It is all formula oriented and all, and it has a pretty decent weightage. So after current, mostly we should wrap up this thing by next Friday. Next Friday, we'll start off with ray optics in the second half at least. Okay, we already done 40 questions. So do start solving current electricity. I hope capacitors is done by everyone. So if it is finish off whatever is pending and start doing by Monday at least, Mondays you have to start doing current electricity. Quite an important chapter. If I have to compare in mechanics, how is work per energy in center mass collisions? That is like current and capacitors. So pretty high weightage. Okay, with that we'll wrap up for the day. Do remember there's a test online till next week, so make sure to give it. So yeah, any doubts, anything you can stay back and ask, or else you're free to leave. I'll see you guys again on Monday, same time. So take care, stay safe.